All right, welcome to another exciting episode here of Advanced Level Chemistry at Spain Park High School. Today is November the 1st, Friday, November the 1st. We're almost finished with the first semester, y'all. It's hard to believe. Time is zooming by. But yesterday we talked about atomic bombs. Hopefully you didn't have too many nightmares last night. But I do want to show you this one little thing that I forgot to. This is the advisor. It's from the Retirement Systems of Alabama. Every teacher in the state gets this. It's a monthly newsletter that they send out. But 2 years ago, October 2022, and I'm not really quite sure why they included this, because it wasn't really relevant to much, but it talks about the nuclear warheads that different countries have, okay? And so here are the number of warheads in the United States, 5,428. Russia has 5,977. Now these are like 25 megaton warheads. What we saw in the video yesterday was a 30 kiloton. So we're talking that these are going to be about 700 times stronger than what we saw the explosive nature in the video yesterday. Just to kind of keep encouraging you on just how good life is here. And others, we got to be worried here. North Korea is probably the one we have to be the most concerned about as far as for us, because they're the crazy people. That leader over there, he really is nuts. Okay, so, and again, he's the one that just tested last week an intercontinental ballistic missile that can carry these warheads. China has 350. Pakistan and India, they'll probably end up, if they ever use one, use it on themselves. They're constantly fighting over the Kashmir area that divides the two of them. Israel has 90, Britain and France. So these are the countries that are nuclear capable. They have atomic bombs. Okay? Just so you can see, and also notice the tally here. Ours are theoretically decreasing. We're trying to, Reagan, we had the SALT treaties where we're no longer testing. We're supposed to be decreasing the number of nuclear warheads little by little each year. But notice that Russia is in the increasing color. We're the only one in the decreasing color. All the rest of these are kind of in the remaining the same kind of state. So just a little tidbit for you as far as keeping you up to date. All right, so now we didn't have a chance to talk about hydrogen bombs. Okay? A hydrogen bomb. It's a fusion bomb. Okay, now, so get your notes out and have this study guide out. Oh, by the way, so the study guide, and you can thank first period, made this decision unilaterally for all the rest of y'all. The study guide, because they want the answers, we're going to be due on Sunday night. Okay, there's a classroom post now, so you'll have to scan your answers to the study guide by Sunday night at 7 p.m. I'm going to post the answers shortly thereafter. This is a 20-point optional grade. Okay, so Sunday night at 7. Now, in addition to the study guide, note that equation worksheet that we worked on. Some of y'all were absent, but we did that equation worksheet where we worked on the nuclear equations front and back. Okay, that's going to be due on Monday, and you need to study those because there's a few on the study guide, but you need to be able to do nuclear equations as well as knowing the notes part. Okay. But that's going to be due on Monday. Does everybody know what I'm talking about, that worksheet that we did all those nuclear equations on? So you're going to physically turn that one into me, but then the study guide's got to be posted in classroom by Sunday night at 7, and I'm going to post the answers to the study guide shortly thereafter. But we can kind of go through the notes and through some of these study guide questions at the same time right now. Okay? So what does it mean for fusion? That it's a fusion reaction. It's put together. So fission is one big atom splitting into two smaller ones. Fusion is two small ones fusing together to make a big one. And so it's going to be hydrogen atoms are fused together to produce helium. hydrogen atoms are fused together to produce helium. Now, in the atomic bomb, the hydrogen bomb, it's going to be deuterium, and anyone know the name of H3? Tritium or tritium, Tritium, tritium. Now this is man-made. This doesn't exist in nature. So the government makes this as well. Okay, but they fuse these together in a hydrogen bomb. It's up to 7 times more powerful. Okay, so these are the 25 megaton bombs. These are the ones that are super powerful. These are the ones that most of our nuclear warheads now are these hydrogen bombs. They're now, we can't use fusion in a nuclear power plant, even though it's so much stronger and gives off so much more energy. The problem is it gives off too much energy. Things get so hot, nothing can withstand the heat. Everything of known material will melt or vaporize in a nuclear fusion reaction. So you may hear in the news sometimes I'm talking about cold fusion. If you ever hear the term cold fusion, they're trying to get fusion reaction that's still not going to be cold, but it's going to be cool enough to where we can contain it, where we find that something that we can actually somehow harness the energy and keep it to be able to use it for productive things. In a bomb, you don't care. In a bomb, you just want everything obliterated. So, but right now, the heat's too intense. Nothing can contain it. All right. Now, why do you think it would take so much energy to start a fusion reaction? What's fusing together in a fusion reaction? In a fusion reaction, what are we fusing? We already kind of said it. What part of the atoms? The nucleus. Okay? The two nuclei are fusing together. Well, what's the charge on each nucleus? Positive. So what do we know about like charges? Do they attract or repel? They repel. And so you have to overcome, the scientists have to overcome very, very strong repulsive forces in order to make those two nuclei come together. So you have to get them going super fast, heat them up, speed them up. You got to get them flying so they can overcome to fuse it. So it takes high energies to cause a fusion reaction because two positive nuclei are being forced together. You can even just say positive nuclei are being forced together. You have to overcome tremendous repulsive forces. Now, in the hydrogen bomb, the way that they get that energy is they use an actual fission bomb as the detonator. So if you have a hydrogen bomb going off, they actually have one of the atomic bombs that we talked about yesterday. That's actually a small one of those on the inside as the detonator, just to create enough heat to cause the fusion reaction to really go big. So, I mean, the little boy bomb type thing is actually a detonator for the even bigger boom. So a hydrogen bomb actually has all three because you have to have a normal explosion to start the fission bomb, and then the fission bomb starts the fusion bomb. So it's a big boom. Now, the sun uses the exact same reaction, okay? Hydrogen is fused into helium. Now this stat right here is going to blow your mind. It's going to blow your mind. Are you ready? It is Friday. Okay, I know that you're just here trying to make it through, but get ready. On our sun, 700 million. That's a 7 followed by 8 zeros. 700 million tons of hydrogen are converted to 695 million. That's 695 followed by 6 zeros. Each second. Our sun is is burning 700 million tons of hydrogen a second, making 695 million tons of helium every second. Yet it's going to burn for another a million years or so. I've heard several million years. I don't know exactly how long it's supposed to burn. I'm just not worried about it. I don't think I'm going to be affected by when it burns out. Okay? Does anybody see a problem here? In that numbers that I just gave you? We're missing some, right? What happened to it? And by the way, how much is missing? 5 million. Okay? 5 million tons of mass is converted into energy each second. I say billions of years. I must have looked that up. Billions of years more. How big is our sun? I mean, 700 million tons a second. And it's going to go for a billion years? And our sun's a small star. Now, take this for a grain of salt. Because there's a preacher called Louis Giglio. And he does, it's not all that religious on this. It's just talking about how big our universe is. But he does the whole thing, it's 12 minutes long, is if Earth was a golf ball. He compares then how big our sun would be, and then he goes and compares 3 or 4 more bigger suns, bigger stars. And just as amazing, compared to a golf ball, how many golf balls would fit in each one and how big. And it's just amazing, and just picking 4 stars out of the billions that are in our galaxy, in our universe, it's really quite amazing. It's worth a watch, okay? But again, it is religious based, but it's not really all that religious in this 12-minute little segment that's on YouTube. If Earth was a golf ball, it'll blow your mind. I can't show it to you in class because it is basically religious, but it's worth a look just for how big our universe is. It's crazy. Okay, so that's just kind of the fusion on the sun. It's the same as our hydrogen bomb. It's fusion. It's hydrogen into helium. So when you go and you look at your study guide, well, let's just finish this and then we'll look at the study guide answers. Okay. So again, notice if it's all cap and bolded. What does that mean?
It's on the test.
It's probably important and for sure going to be on the test. So somebody, Jacob, read that for us. Roll out.
The source of all energy in nuclear reactions is the conversion of mass to energy. The products of a nuclear reaction always weigh less than the reactant.
Okay? So the law of conservation of mass does not hold true for a nuclear reaction. The products always weigh less than the reactants. Where does the mass go?
Energy.
Turns into energy. E equals mc squared. C, okay, it's on the previous page. C is the speed of light, 3.00 times 10 to the 8th meters per second. You square that. That's 9 times 10 to the 16th. 10 to the 16th is a big number. So when you multiply that by the mass, it takes a little bit of mass to generate a tremendous amount of energy, which is why those little tiny fuel pellets can generate so much energy for an atomic bomb or for a nuclear power plant. Okay? Just a little bit of mass generates a tremendous amount of energy. And then just lastly, these are the things we talked about yesterday, but it's just here it is in the notes just so you can highlight it. These are the horrible things of radiation sickness and even the horrible side effects if you have to undergo cancer treatment. I just have so many friends that right now are just struggling and having to do some of this. It's just bad. It's just bad. I hate cancer. I sure hope we one day can figure out a way to not figure it out. Anyway, it's a horrible thing. So we just need to be just aware of the side effects, okay? All right, so let's look at some of the key things in this study guide, just to kind of make sure. So I'm gonna kind of look right here in the middle. What is the difference between fission, number 8, fission and fusion? Okay, now I strongly recommend that you do this on a separate sheet of paper because there's really not room in between spaces there to do that. Some people are trying to cram it in, but for your purposes, it's probably just so you can do it better on a separate sheet. But number 8, now if you just want to put this in here on this sheet and then transfer it, but what is the difference? What's fission? We just already said it. What happens in fission? What happens in fusion?
Fission you break apart, and fusion you put together.
Okay, she said it perfectly. You all hear? Okay, so big atoms split apart, small atoms you put together. So uranium is one of the big ones. That's one that goes fission. Hydrogen is the smallest of all. That's the ones we're talking about fusing. Okay, but why is so much more energy required to initiate fusion than it is fission? Okay, so what's repelling? Of the what? The two nuclei have both positive. So in fusion, you have to overcome strong repulsive forces. It takes a lot of energy. You got to make them go very fast. Why don't you need it in fission? What are you bombarding the nucleus with in fission?
Neutrons.
Neutrons. What's the charge on a neutron?
Negative. No, neutral.
Neutral. So is there going to be any repulsive forces?
No.
So what is the function of the moderator in a nuclear power plant? What's the moderator do? Now that's the control rods. The control rods control it. It does what? Slows down the neutrons. So not only do you not have to speed them up, you actually physically have to slow them down. So there's no repulsive forces. So the neutron has to be even slowed down to be absorbed because it's neutral. Whereas fusion, you got to put two positive things that combine them together. So it takes a whole lot more energy to do that than for the neutron that's neutral that doesn't have to overcome any of those forces. Does that make sense? So, all right. So what's the reaction in an atomic bomb? Is it fission or fusion? It's fission, okay? And then what's the fallout?
Like the stuff that stays in the air.
It's the leftover dust, right? Remember, so fission, you break the big one into two smaller ones. Are the two smaller ones stable? No, they're still radioactive as well, right? Neutron-rich, beta emitters. And so they're all up in the dust. Some of the unreacted uranium that didn't have a chance, remember only 15% actually blew up. And so you got the leftover unreacted stuff, and it all goes up in that big mushroom cloud, and then the wind just blows it wherever. So it's just this radioactive dust that just tends to fall wherever the wind takes it. Okay, that's your fallout. Some say it's going to cause a nuclear winter, that it's going to block the sunlight, and if we had a major nuclear war, and then so everything would get cold because the sun would be blocked by all the dust and everything up in the air. Okay, so in a hydrogen bomb, is it fission or fusion? It's fusion. And what's the reaction though? What combining into what? Hydrogen into helium. Okay. And which is more powerful? Atomic or hydrogen? How much?
7 times.
Okay. All right. So then we just talked about all this stuff, so you can pretty much fill all that in. There's equations and your half-life and all that. Okay. So you can have the rest of the time now just to work on this study guide and see how much you can get done. Okay. And then, so on Monday, just remember you're going to turn in that equation, and you need to make sure you know how to do those nuclear equations. There will be a whole section on the test of writing equations. There's 30 multiple choice questions, one short answer question, and then a bunch of equations to write. All right? All right, y'all have a great weekend, and go Jags.